ICTP-SAIFR.org. So if that applies to you, please do it today. Do not forget. Quite important. We're going to get started in just a minute. And today's lecture will be strictly on the Blackboard. So most of the ideas will be covered in a series of papers that I'll share with you. And if people want, I can also just, it's a little bit rough to read my handwriting. So I could try to scan my notes, but I also will take some pictures of the board afterwards, and I'll probably just post those. Okay, or you can do it yourselves, but if everyone's taking pictures in the middle, it gets a little odd. So we'll try to remember to take some pictures before we race. Okay, my clock says 10:30. So today the lecture is going to be on heterogeneity and its consequences. So that's the theme today. On heterogeneity and its consequences in epidemic models, and just as some references, and I'll just sort of keep this here on the side, and then we'll try to spend most of my time on those center boards. A lot of this work is going to come from a series of papers, some of which I've been involved with and some by others. A recent paper in Journal of Theoretical Biology, 2021. There's some related work, Journal of Math Bio in 2023. There's older work. And this is not one I read regularly, Math Models of Natural Systems in 2012. And there's even older work by Dwyer. Okay, so there's a sequence of articles here, and there's more. This is just a subset that hopefully will get you oriented if you're interested. And the idea is that all of these papers in one way or another confront what we've been dealing with, which is these SIR model classes and their extensions. And again, we've already seen how these work in different ways, where there's some attack rate that goes from susceptible to infectious, and then there's recovery removal to R, and one can add various components to this, right? So obviously it's not just an SIR model. We could make it an SEIR model, or an SEIAIS R model, or variations, right? But no matter what these variations are, they all have a feature that everyone in the population has the same characteristic rates, right? The same rate of recovery and the same attack rate. And one can deal with this in different ways. One of the ways that these models tend to deal with things is they turn whatever the parameter is into some explicit function of time, because there's a lockdown or people start to wear masks. And that's also fine, right? Today's lecture is not meant to critique in some ways these other models. I've worked on those other models and I think they can be instructive, but they leave open some gaps. The other way, so that's one way to deal with this issue, is sort of make things in time, but it doesn't deal with the heterogeneity issue. Another way that these models tend to work is you take the susceptible population and you split them by age or activity or location or some combination. So you take this population and then assume, as I showed you in this Britain model, where you have age differences, maybe with respect to the values of beta, and you also have activity differences, and then depending on whether or not you allow individuals to interact with other individuals assortatively, meaning people of the same age tend to interact with people of the same age more so than other ages, you can get more complex models. I mean, as you probably have realized, though, these get more realistic, but you sacrifice something in the process of making them more realistic, is that you lose some analytical tractability. It's hard to sit down and reason. And I also want to make a difference between an analytical expression. So sometimes in other disciplines, you have an analytical expression, and you declare success. But sometimes the expressions are themselves just like a calculation. They're long and complicated, and it's not clear what the insight is, right? So not only do some of these other models not lend themselves to analytical tractability, they're also missing some insight. Why is it that the outcome turns out this particular way? And one of the themes I think you've seen this week, whether in the Britton article and others, is that when you add heterogeneity, somehow this final size isn't as big as we tend to think, or there may be even other changes that are happening in the system. So the theme that I'm going to try to do today is to give you some insight. Now, is the model that I'm going to present today complete in the sense, is it absolutely representative of what goes on in natural systems? No, but it captures some essence of what I think are in these other models. And we're actively working on extending them. So I view this as an active area of research. This is why it's on Thursday and it wasn't on Monday. Okay, fine. So what I want to talk about today is what I consider a mesoscopic model, and I'm using the word scopic model to differentiate from some more microscopic model where I might treat every individual and have some individual-based model, or some mean field or macroscopic model where I'm neglecting all of these differences. So I'm going to choose something in between. And of course, someone's already asked me about differences between this sort of approach and network models, and we're actually trying to see how much we can reconcile things. I think there are some productive analogies and ways to link them. But I'm going to take this SIR model and add a little subscript called epsilon to denote the fact that I'm going to add some structure in some way. And this epsilon is going to refer to susceptibility to infection, and I'm going to assume the population is heterogeneous, so not everyone has the same, whether you want to call it vulnerability or susceptibility to infection. And in other words, I'm taking this population of S and going to structure it such that I have different bins of individuals, each of which carry with this different susceptibility to infection. And if I were to add up the number of individuals in each of these bins, or take an appropriate integral if I make this a continuous distribution, I get the total number of susceptible individuals in the population. Okay. And like the SIR model, all of these individuals can flow in and become infectious, and then they can recover, and there's no reason why I'm drawing these boxes in different ways. And I'm only going to focus on heterogeneity in this first part. There could be heterogeneity in recovery and other things. And what I'm trying to say here is that the way these transition is that there's some attack rate beta, but it's modulated by the value of epsilon. Okay, so individuals in this category of epsilon small have very little chance of being infected, and people with epsilon high have a higher chance, and the mean here in this example, we can set it up to be 1. Okay. So in this formulation, and we'll see how I'm using the board. These don't slide up. No, this isn't a double slider, which would be cool. So in this formulation, instead of writing the derivative right away of the total number of individuals, so here we have epsilon, what I'm going to write instead is going to think about what happens in each one of these bins or categories of susceptibility. And I'm going to use the same rules as before, that we're going to deplete these individuals because they're coming in contact with infectious individuals. But again, this is the crucial point, that it's modulated by the value epsilon. So it's not the same for every bin. Okay? And the total number of infectious individuals then, and I could have kept track of this and made some relationship, and we have a paper that just came out that did this, and then you have to have correlations and a whole bunch of features, so I'm going to put that to the side for now. And I guess I could also write, I don't even remember where this came out in. I think Harris et al., I think it came out in Epidemics. And I think it came out this year. I can't even remember. The years are blending into each other. Okay. So here we could take an integral of all those individuals who are susceptible with different values of epsilon who became infectious. And so we add all these up to get the total number of new infections, the incidence, and then there's some recovery, and the R dot as before. It's just the accumulation of those who've recovered. And I just want to make a couple housekeeping notes here that the total number, S of t, and I'll try to make, it's hard, the notation here is a little bit tricky because sometimes I'll use S of epsilon. If I don't use S of epsilon, I'm probably referring to the total. I probably should have called it something else, but that's what it's going to happen, is the integral of all these bins across the different categories. And keep in mind that at the beginning, S of t equals 0 is going to basically be 1, and this is the integral d epsilon of S of epsilon comma 0. So we have some initial distribution. Almost everyone is susceptible. And over time, the total number of susceptible individuals can itself change, but so can too the distribution in the groups. There was a question?
Is there an integral of the second one?
Yes, this is an integral.
And why?
Because the total number of infectious individuals are those.
This is the total, not the
Yes.
rate.
It's the total. And again, this will be our little reference point that I'm only distinguishing individuals in the susceptible category based on the susceptibility, but once they're infected, I'm assuming they all have the same features. So in this paper, we don't assume that, but it's a lot more work, and I'm not going to do that today. Right. Absolutely not. I just forgot to write it. In my notes, it has a d epsilon, which sometimes I'll write to the left and sometimes to the right, but yes, there's not a reason, just an omission. That also explains why, is that an integral? It's missing some differential. Right, okay. So we have this set up here for this problem. And so in this model, we might ask, how do we expect an epidemic to unfold? Is there going to be any difference? Have we just made this extra category and nothing's really going to happen? What's going to change? And is something fundamental going to change? Or can we learn something maybe somewhat general about how dynamics might unfold with heterogeneity by using this kind of formalism? Okay. And there's some other features here that I'll refer back to at the end that are limitations. But again, I'll circle back. So the first thing I want to do is sort of the brute force approach. I'm not going to brute force my way through this whole lecture. Are there questions up there? No. But I still want to just treat this term directly and just get some insights from it. So if we view each category of the population, the subpopulation whose susceptibility is epsilon, then we should be able to focus in on just that particular group right? This is just looking at that one component. And I should write, yes, okay. Everything is a function of, the big I and the big S are functions of t. I'll just sort of omit them. So we might be interested in seeing how this is going to change with time, and you'll notice that we can do the following. And now we can take an integral on both sides. I've just moved things over. So we get something like the log of S of epsilon comma t plus some integration constant is equal to minus beta epsilon, and I'm going to write IC of t, where IC of t, you can think of this as the total number of prevalence days. It's the cumulative 0 to t dt of I of t. So it's this total accumulative, it's sort of an accumulation scalar of the force of infection over time. Okay? So we have this, which in other words can be written as S of epsilon comma t. And you can see at the beginning there's no infection, so we just have S of epsilon comma 0 times e to the minus beta epsilon I cumulative of t. Okay? What does this mean? It means that once we add heterogeneity and we've modulated the degree of infection by this value of epsilon, that if we were to start, and now I need the other color. I had one there, don't need to keep bringing them over. If we were to start, for example, with some initial S of epsilon comma 0, here we are, you can see that over time, each of these categories, these bins of population, will have dropped exponentially, but modulated by this factor epsilon. So I need to have big decreases here, and then I will try, which is impossible for me to do, but I think you get the idea, that these changes will go exponentially down as I approach epsilon 0, which means that over time, I'm going to have something that's going to look like that. And this infection process is sculpting this distribution to the bottom left. Not only are there fewer individuals who are susceptible that remain, but clearly something is happening with respect to susceptibility, right, as it's depleting this part of the distribution more than the left part. Okay? This also applies if for some reason we had had a different initial, let's say it was more homogeneous. And again, there'll be big decreases on this side, big arrows. You can see this is just me. And then these arrows get smaller, smaller. I can't even draw them. This is S of epsilon. The arrows denote, thank you, the ways in which I expect S of epsilon t to be different than S of epsilon comma 0. So here is this white curve is S of epsilon comma 0, the initial distribution. And then this yellow curve, which gets close and then starts to really diverge later, is S of epsilon comma t. And the reason why I'm making it diverge more to the right is because you see I drop farther as epsilon increases. Okay? All of them share the same, they've all faced the same pandemic. Cumulatively, they share beta and IC of t in common. They differ in epsilon. I'm going to make this more intuitive. Okay, so this is an idea that perhaps this process is doing more than just decreasing the total number of susceptibles. It's changing something about the shape. Okay? The problem with this kind of approach is that it's somewhat procedural. It seems like I'm making calculations and you have to take some guesses. So I want to try to do something a little bit more general, but I do want to keep this in mind, and I'll return to it later. And it's actually going to be important. Yes? These are just two examples of potential initial conditions. Case 1, case 2. Yeah, they're just examples. Other questions? Okay. But now I want to go to the population as a whole. And keep in mind that maybe we can say something a little bit more general, but I want to look again at the total population of susceptibles, which is the integral from 0 to infinity d epsilon. If I put it at the beginning, I'll remember not to forget it. D epsilon s of epsilon. That's the total number of individuals. So now I can ask the question, well, how did the total number of susceptible individuals change with respect to time? Right? What is S dot? Well, that should be equal to 0 to infinity d epsilon partial s of epsilon with respect to time. Really, it's a full derivative. I don't have any change in epsilon, but that's okay. So my total population will be changing because the subpopulations are changing. In other words, I can take this integral from 0 to infinity d epsilon, and I have to recall over there that we have beta epsilon I s of epsilon. Okay? Which I can write by pulling out this minus beta I as the integral from 0 to infinity d epsilon epsilon s of epsilon. Everyone see that? Hopefully it's clear. But this looks like something. Anyone recognize what a term like this could mean? The mean susceptibility, but not quite, because I have to divide that by the integral, right? So the mean susceptibility, but you definitely recognized it, should be the integral d epsilon epsilon s of epsilon divided by, because remember the total can change, right? So I only have the top part there. But I can then replace it and write that the change of the total population should be minus beta I. And you can see that this part here is nothing other than the total population of susceptibles times the mean susceptibility. So I can write this as S epsilon bar. So now we have a slightly different equation at the level of the population. Rather than just the product of I times S, we have the product of I times S times susceptibility. And you could think of it as being that beta is changing. Beta is whatever it was, the sort of attack rate times the mean susceptibility. But if the mean susceptibility is going down with time, so too is the attack rate, right? And the other key point here is that the mean susceptibility is not a constant. It's itself a dynamic variable, okay? So what our next objective is, and this is I have to save this one. There's some things we're going to have to save. Oh, I'm supposed to take pictures of boards before they go away. I mean, I also, do you want me to save the boards, or do you want to just have the copy? I have this all, I'll scan this. Yeah, I think, I mean, the notes will have a few errors, but they're in an order, so, you know, people can do what they want. So, this is not that important. I'm obviously saying things that are slightly different on the notes, but you get the idea. I'm going to erase this. Okay, good. And I just want to keep that in mind because we're going to have to collect some important parts, and we've already gotten one of the important parts, which is now that S dot is equal to minus beta I S epsilon bar. Okay? Now, we could go right away and attack the epsilon bar because you can see once we define this, we could just go and take a derivative. I'm going to do that, but I want to do one other move first because I still want to build up insight as to what we think should happen. And before I do it, I want to go back to a point that I made briefly in one of my lectures this week. I don't remember which one it was, maybe yesterday's in the morning, which is I want to think about the features of the next individual to be infected. So if I have some epsilon and S of epsilon, and I'm just going to imagine that it's like this, and here's my current mean. who's likely to be infected next? Remember, we already talked about the fact that the probability of infection, or the attack rate, is scaling with epsilon. So down here, we're unlikely. Here, it's very likely if you have a high epsilon, you're going to be infected, but there are very few, right? So somehow, something in the middle may be the case. If you remember, I think I drew this, and then I drew something like, no, I wanted to get this other color. Something like this, which was epsilon s of epsilon, right? Okay, so let me define epsilon d as the draw of susceptibility, and I'm going to define epsilon bar d as the average susceptibility of the next individual to be infected in this process. Okay? And I can write this as the integral d epsilon of the value of epsilon times the probability that you're drawn. I mean, that's a pretty simple way of writing something, right? The probability of an event times the value of the event. Okay? Where the probability of drawing this is equal to epsilon times s of epsilon over, we have to normalize it, integral epsilon s of epsilon d epsilon. And in my notes, sometimes I'll forget the d epsilon. I move too fast. So just assume whenever you see an integral, I meant to put d epsilon. Right? So this is definition of probability. Integrates to 1. Good. But you can notice something here, that this on the bottom is just epsilon bar times s. So which means that the draw on average is the integral d epsilon squared s of epsilon times epsilon bar s. Yes? D is for the draw. I'm drawing a new value from the population. I'm just using it to mean the draw. Not to draw this way, but to, like you draw a card. Sorry, it's getting warm in here with the sweater. Okay. Right, where was I? Yes. Okay, in this case then, the average susceptibility when I draw the next one can be written as this integral of epsilon squared s of epsilon divided by s, which is nothing else than the average value of epsilon squared. Divided by the mean value of epsilon. Now I want you to recall, and this should be apparent, that if I have some variance, that's just the average value epsilon squared minus the average value squared. So I can rewrite this draw as just sigma squared epsilon plus average value squared all over average value, which means I can write this as the average value plus the ratio of the variance to the mean. Now, this is nice because I haven't even done anything with particular choices of distributions, but I've made the claim that epsilon, the average draw, is going to be greater than the mean. Anytime there's any heterogeneity, we have a variance, right? Strictly positive. And so therefore, unless this is precisely a homogeneous situation, in which case there's only one thing to draw, any heterogeneity means I'm always drawing something on average that's greater than the mean. And if I'm drawing something that's greater than the mean, this means the mean has got to go down. Okay, I just took away, I have a bunch of numbers. I took away a big number. Therefore, my mean is going down. Okay? This implies that this infection and sculpting process, which I've shown here, and again, which you could do technically using this, I could calculate my mean, right? I could just go ahead and do the calculation. But here I find this more insightful, that what's really being operated on is that this draw is going to pull down the mean value, because on average, not every time, but on average, the next person to be infected has a susceptibility greater than the mean. That's part of this heterogeneity, and it's also part of the idea that it could lead to confusion, because early on the idea was, well, maybe people with SARS-CoV-2, it was the people who are out the most, and that when they were already infected and therefore immune, then the disease would go away, right? And so there is something to that, this notion that people are infected early depending on the disease. Respiratory disease may be those most inclined, not inclined, but in the sense of most vulnerable to infection, because they're out more, interacting more, and so on. Okay? Good. Yes. Right. There's a technical aside here, which I don't know if I want to do, but just maybe, I don't know how long I want to do this. Just if you want to actually do this calculation, I made a claim before, so I'll just sort of state it. Though it does come up a little bit later, so maybe I need to do it. So we have a kind of a technical aside, but I will invoke something later, so I guess I should do it. If we start with a exponential distributed susceptibility distribution with mean epsilon bar, then this draw is going to be equal to integral d epsilon squared e to the minus epsilon over epsilon bar. I have to pull down this, right? And I'm going to do this initially, so now I have epsilon bar squared, and big S is 1, okay? This integral on top can be done by parts. Can you just trust me that I can do the integral by parts, right? Because I take u, which is epsilon squared, du is 2u d epsilon, dv is this, and I do the math. And you end up getting equal to 2 integral 0 to infinity of d epsilon e to the minus epsilon over epsilon bar, right? Yes. But this whole thing is equal to then 2 epsilon bar. So in a specific case, and that's where I told you before about a specific case, the draw is on average twice that of the mean, but again, that is just the particular case of the exponential distribution, but I'm going to use that particular case in a few other circumstances. And it's very warm, and the odds of me doing this next move correctly seem to be very low, but I'm going to have to do it because it's very warm. Hold on one second. Any questions at this point? Very warm up here. Okay. Got my cool tree shirt on today. Let's see if I can put this back on. Good. Let's see if this part gets back on. Reverse order. No, I managed to tangle myself. There we go. Okay. Yep. Not that important. Mean the value of 2. Yeah. Yes, they're arbitrary. Yes. The 2. Yeah, no, that is a particular, it's absolutely correct. And I mean, there are different ways in other formulations people, for convenience, would like to use a different monotonic function. And I like, in some sense, this, especially pedagogically, because it organizes thing by epsilon, and then you just restructure S, right? Because I can organize by the way in which your vulnerability scales, and maybe depending on how I do that function, I have to change my S of epsilon. So this particular value 2, as I said, I'm just going to use, just to note that one can do that calculation. That is not the general result. The general result is the draw is greater than the mean, and that's going to be the takeaway, okay? Okay, good. So now I need to start erasing more things. I want to keep this part because I feel like it's important for you all to look back and forth, but I am going to start to erase entire boards. So are there any questions about this stuff before I move on? There's only so many boards here. No? Okay, so our objective now, remember we held on to this. Let's keep up where we were. I know there's a lot of math here today. We had found a new relationship between S dot, rather than just being minus beta IS, we also had this E average susceptibility, but that is a dynamic variable. And I could have just, again, as I said, attacked it, but instead I just wanted to show you why I think it's going to decrease. It must decrease. And now we're going to explicitly derive it. Okay, so I'm going to erase this component. No complaints. Away it goes. Okay. Goodbye, nice board. It was a good board, but it's gone. Okay. So now let's go back and write down explicitly, recalling that the average susceptibility is going to be an integral of epsilon S of epsilon over the total number of susceptibles who are left. And again, I'm just trying to use, if I don't put explicitly of epsilon, it's the total number. So now I want to take a derivative of this, and I have f divided by g. So if I want to take a time derivative, I'll have to take df dt g minus f g dt divided by g squared. Okay? So that's all I'm going to do now. So I'm going to take s times integral d epsilon epsilon minus this thing, but I need to have s dot and is all over s squared. Okay? So I've kind of done the standard thing, but keep in mind that we can replace this, hopefully. Oh, that was, no, good, we didn't lose it yet. Here it is. So we know what to do here. Every time we see this partial, we replace with this, and we get minus beta is, and I'm going to keep my s squareds separate, times the integral d epsilon of epsilon squared s of epsilon. Hopefully we're still on track. Good. And then minus s dot, which we have over there, becomes a plus beta is epsilon bar. But this is nothing else. Just remember, if we divided by that, we would get epsilon bar times s, so we get another epsilon bar times s, and we have to divide this all by s squared. Okay? What I hope you can see is that we can get rid of this and this, and this, and this, and this, and we're left with minus beta I times what is clearly now the average value of epsilon squared. And here, the average value of epsilon itself squared. Which means if I pull out a minus beta I, we get the average value of epsilon squared minus, because of the double minus makes a plus, average value of epsilon squared, which means that the change of the mean susceptibility is minus beta I times the variance of epsilon. Okay? This is a nice result in the sense that I think it tells us something about how the infection process operates, even in terms of now its speed. First, you have a sign. It's always going to be negative, right? So it's non-positive, only when the variance is 0. And I don't know if anyone has seen an equation like this before in an evolution class or pop gen class. Anyone seen an equation like this where something always goes in one direction as proportion to the variance? Anyone ever heard of Fisher's fundamental theory of evolution before? Say again? Well, sure, a random walk could do something, but if that's the magnitude of something, sure. But in Fisher's fundamental theorem of natural selection, you have a process of heterogeneity, right, with different replicators that have different fitness. And the change in fitness is going to be proportional somehow to the variance. Right? So it's really heterogeneity that allows something to increase. Now, in that idea, in that particular space, the idea is that fitness somehow always increases. So it's, as long as there's some variance, it always is going up. That's not true if there's some density-dependent feedback or other features. So again, this is true insofar as I've set up a bunch of rules here at the beginning. Most prominently, once you're in one of these categories, you stay there forever. You don't move between the categories. Right? Once you allow, and I'll just mention that at the end, and we're trying to work on these, once you allow, in some sense, social diffusion, rather than just intrinsic heterogeneity, then a lot of different things can happen. Nonetheless, though, this tells us we have now two coupled equations. This doesn't seem so great for us yet. We haven't closed things. But we're getting closer potentially to understanding how the system as a whole might operate. Okay? And again, it says something about the way that this may lead to something predictable or general. And certainly it says that we now know from two different angles, this draw and now even looking at the mean, that we expect the mean to decrease, right? This is the reason why, and this is how it decreases. Okay? Good. So now I'm going to do something specific. There's a more general thing one can do, but I'm going to use the specific as a way to attack a general issue. Okay? So I'm going to make a distributional assumption that doesn't generally hold, but I'll use it because it's going to help put some wind under my sails, as it were, to get a little further along. So I'm going to erase this board now. Okay. Good. So we've gone from defining the problem to having some intuition of what happens with heterogeneity, that because of heterogeneity, things that are more likely to be infected get infected early, which actually changes the rate, right? And not just depleting individuals, but transforming the distribution of vulnerability or susceptibility of the individuals who haven't been infected yet. Okay, and let me move that one. I've already collected it, and I'm going to need a little more space here. I'm going to erase this, but I put it over there. Okay, so, right. And anyway, it's already there. Okay, so now I want to make a specific choice, and again assume that S of epsilon eta minus epsilon, epsilon bar, 1 of epsilon bar. And then ask the question, well, what is the variance? And I just did an integral over there, and I'm not going to do it again, but the variance of an exponential distribution is the mean squared. Okay. So now we actually have a chance to do something. And I would just want to point out to your point about specifics, if I had used the gamma distribution with the shape factor, I'd get other types of results. But I want to show you the kind of results you get. Okay? So now we can take this idea that the susceptibles are being depleted but the rate of that depletion changes as the mean susceptibility changes. And the susceptibility is also changing, and it is going down with respect to the variance, but here, in this specific case, it's a function of the mean squared. And now you can notice that there's going to be a coupling between the two. If I take the ratio of these two things, ds, d epsilon, as the infection progresses, this cancels, and you get S over epsilon. Bar. And this implies, I don't know if I have enough space, these aren't very complicated things, that if I were to take the integral here, we end up having ds over s equals d epsilon bar over epsilon bar. I think we know what to do there. Everyone following me still? Which means that log of s goes like log of epsilon bar, but at the beginning, s is 1, epsilon bar, we can just by definition say 1, right? Which means that if we exponentiate this, we see that S of t should be equal E bar of t. In this specific case of an exponential distribution, if I have 70% of individuals remain susceptible, the average susceptibility has dropped to 70% of the initial value. So they're tracking each other. Now, for other distributional assumptions, that is not going to be the case. Right? But in this particular case, you see that we then now have a closed form not for the two coupled equations, but really just for one. And this implies, if I were to replace it, if this is just tracking, this implies when S of epsilon is something like e to the minus epsilon over epsilon bar initially, then S dot is minus beta I S squared. And if I had made a different assumption, for example, that this was gamma, I could get something like 1 plus k, a shape factor. So there actually is a notion of generality here. It has to do with the relationship between the mean and the variance. And it doesn't always work. Right? Okay. So this is, I think, kind of neat and insightful because it's saying that when you have heterogeneity and you're tracking the total dynamics of the population, that the core model may no longer be the right model. Right? Even though I have the same sort of classic contact structure, it's just modulated by this rate function. When I look at the population as a whole, we have a different nonlinearity. Right? And that also suggests that maybe, because we know populations are heterogeneous, we've made some extremal assumption and the SIR model is just moving too quickly through a population because we've made this extreme assumption that there's no variance. Everyone is exactly the same. Okay, so now we have, and I'm going to play with this particular model to see what its consequences are. And again, I don't have to go all the way to 12 o'clock today. I mean, I have a few more things left, but I'm just trying to get the core ideas. We have S dot is minus beta I S squared. I dot is beta I S squared minus gamma I. And R dot is gamma I. And of course, this equation reflects the fact that if I have this heterogeneity and I had initially exponential, if I didn't have exponential, this number 2 is not universal. Right? That's a specific choice. Okay. But we can start to go back to where I began early on. Like, what's the speed of this epidemic? How big should the epidemic become? So we could ask the question near 1, 0, 0, I dot becomes beta I minus gamma I. In other words, the speed is just beta minus gamma, as it was before. Or R, if I pull out a gamma, is just the classic result for the SIR model, that the speed relates to the basic reproduction number. If it's greater than 1, we have a positive speed, and the time scale is set by the recovery period. Okay? So that's good, and you might wonder, why did we do all this mess here? It's exactly the same as before, right? But now let's ask the question about when and what is the herd immunity threshold? When do we expect, if this were some dynamic of takeoff, when do we expect it to turn back down, right? So if t, if this were I of t, and we figured out this is beta minus gamma, is characterized as that liftoff, when do we get this point of turnover? Well, you can see it's when I dot is 0, and again, this model doesn't have the kind of behavioral feedback so that you can get plateaus that occur even when most people are susceptible. So in this model, in which people don't change their behavior, but they have these intrinsic differences, we end up getting that we reach our peak when S squared equals gamma over beta, or in other words, when S is R naught to the minus 1/2. The classic herd immunity threshold is 1 over R naught. Right? So what does this mean? If we were to put 1, R naught, herd immunity threshold, and we could think of this as being, we could also look at how many people haven't been infected, which is 1 minus 1 over R naught, right? That's how many people haven't been infected yet when you reach that threshold. Approximately, I mean, there's also the infected people, so it's not quite true, but I'm going to plot it in this way. So we could think that the herd, this goes something like this, whereas when we have heterogeneity, it's going to be weaker. So this is classic heterogeneity. And the more heterogeneity we have, the farther this goes down and gets suppressed. Right? So for an example of 2, it's 1/2, right? Or you can, let's do even 4 is a better example. We would get the herd immunity threshold when R naught is 4, we have to get 75% of the population infected before we stop and go down. Here it'd only be 50%. Okay? So it's less. So this implies that because you're sculpting the distribution, you end up not just depleting susceptibles, but depleting the class of susceptibles that are most likely to be infected and then keep their infection going, which means you stop it earlier. Right? And this is, in my view, the reason why the work of Britain, which I mentioned the other day in Science, that had this agent activity structure, which was a result of a computation, is happening. Is what's really happening is that by having the people with most activity infecting each other early, you're depleting not just individuals, but if you were to look at seeing who's left, you find that it's the low activity people who are left, and therefore it's harder for the disease to spread. Okay? You have a smile. There are some particular choices I've made. In the paper, we go through other choices. Again, I would claim that writing it in this way is not problematic, but any other, you then loading up how you make your initial S. You might, in another paper by Beresticki, we chose a different value of epsilon, and then for various reasons were made to kind of accommodate some of the mathematics. But if you wanted epsilon squared, for example, I don't know, it's fine. You like epsilon squared. Then your S of epsilon has to change because the number of people which scales their attack rate has to be different, right? So I like this way, again, pedagogically, I think then you have to load S of epsilon, and again, this conclusion about the squared has to do with my choice of epsilon and my choice of my exponential distribution. But if I change that, for example, that's not me, If I change that somehow, then yes, this particular conclusion changes. But this notion of the herd immunity threshold lowering would remain, just because, for the same reason as before. Yep, question over there. So, no, let me just clarify that here, because at the start, the epidemic seems to take off as usual. So you don't have an indication that this is going to happen. So it's another way in which heterogeneity can also lead to the wrong predictions about final sizes. If people behave differently or have different vulnerabilities, then it's often people with greater susceptibility that are infected earlier, but you won't see that yet early. So again, this implies, kind of like I said the other day, you may overestimate the impact if you don't include heterogeneity. Okay. Yep. Correct. 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 So that's why I wanted to do that first. Yeah, and this is this point which I wrote in this variance. Yes, correct. Right. That's why I like doing that first before just doing to the calculation, because I think that is the right intuition. But now I want to say one more thing. I think I have time to say maybe just one more thing. Any questions beyond those that have been raised? In this Rose paper, there were some efforts to do some fits, and again, this is also similar to what Gomez et al. Had done in some of their fits. And the danger of these fits, and again, I've tried to stay away from some of the fitting, though we do it because reviewers want it. We all ask each other for it. The problem is that you make an early fit, and then you never predict when there's the endpoint correctly because a new variant arises, people change behavior. So yes, you can fit things, but I caution at the present that I'm not sure we're at the point where we know when the turning points are. So as long as you know what you're doing with fitting and you're fitting in a limited range, then yes, you can obviously do these fits. So we are working on ways, right, to take this kind of framework and make it also dynamic. Well, there are different ways that this could be dynamic. First of all, even if you buy into this formalism, there's no reason why the beta has to be constant or gamma has to be constant. And then the other, I think maybe even more profound issue is that there's no reason why potentially we can't have diffusion, social diffusion between categories. Now, maybe you say there's limits. You know, if I view this as partisanship in the US, someone who's on one party is not going to diffuse over in the next year to become the other party. Maybe some fraction might. So this is in the limit of the absence of this sort of susceptibility diffusion, but you could add it and then new things can happen. For example, in this case, you always get one epidemic and it always goes down, but it's just not as big as it would have been. If you add social diffusion, then your susceptibility gets down because of sculpting, but it relaxes back and you can get oscillations. So there's new categories of things that can happen when you add other features. So just trying to get you a piece of the puzzle today. Okay. Let me erase this session. There's one. Is it okay? Yep. Yeah, well, that's our job to be sure to communicate nuance. I mean, I really, you're right, but that's why earlier in the lectures I said that these heterogeneous models always make this prediction, but they have a lot of assumptions. So Fisher's theorem of fundamental theorem of natural selection is true if you agree with all of the assumptions, okay? So you are right, and we must be cautious, and that's why I am trying to be cautious, saying that this, for example, has, I said, no social diffusion, no time, also no reintroduction. So, for example, maybe the initial outbreak, but if it gets reseeded, then you have another outbreak again, and you could progressively keep filling things in. Okay? So there's a few papers in this space, and some of them are referenced in Rose, both some of the fits and other work showing how final sizes are often lower. But look, for SARS-CoV-2, with everyone naive, by the end, it wasn't one wave, but the fraction of individuals who were infected, quite high, right? But obviously, vaccines change things. Let me do one last thing here today, which is I want to go back to where I started, which was the distribution, and just revisit it one last time. So I'm again going to use the specific choice. I apologize, the specific choice of exponentials, just it makes it a little bit easier. And we're going to imagine that initially we had some exponential distribution such that the integral d epsilon S0 of epsilon was 1. Okay, so I have this initial exponential distribution. And I've already showed you that because we don't have this social diffusion, I have some initial, any focal value of susceptibility is basically acting independently. And each one of these, if I think about it, you can see that we had already, as before, some exponential decrease, right? So we've already done this and said that S of epsilon comma time should be S of epsilon comma 0 e to the minus beta epsilon, this I cumulative with respect to time, right? This cumulative pressure. So we've already did that, and that was the first thing I did at the beginning. But now I want to take a ratio and just compare one tranche to another. Right? So I'm going to just compare what's going on in the two, and I'm going to try to use the color here. Okay. So now I can take the ratio of these two things, and I just want to point out here that I could also write this piece, because if it's initially exponential, I think you agree that S of epsilon comma t will be e to the minus epsilon 1 over epsilon bar, right, plus beta IC. Hopefully I did that right. But that also applies to this one. S of epsilon prime comma t is e to the minus epsilon prime. And this is the same stuff. Which means that this ratio, the ratio between them, S of epsilon comma t divided by S of epsilon prime comma t, is equal to e to the minus epsilon, really, delta epsilon times 1 over some new characteristic value. In other words, we still have exponentials. So the infection process sculpts the system such that we have an exponential distribution whose value is, let's see, it's easier to write this way. I could invert it, but you get the idea. So we are left with a distribution that in some sense is an eigendistribution of the process. The host would like you to unmute. Am I muted? Am I muted? Okay, I'm sorry for those online if somehow I was muted. I don't know who is muted, but maybe you can hear me now. So the point is that you have this initial distribution, and this doesn't just apply for exponentials, it also applies for gamma distributions, so things that would probably be more realistic, that there are going to be eigendistributions of this process, that the shape parameter remains the same, right? And so this goes back to this value. You could have, in gamma, you have a shape parameter, and you just get a different exponent here. As long as the ratio of the variance to the mean remains the same in the process, you can end up writing down these sort of mean field-like dynamics, but the nonlinearity has now changed. So this isn't always the case, but in the paper, we show some examples of how distributions can be shaped towards these eigendistributions. And it's a challenging thing to get at, limiting distributions and so on. Right. So I think those are the main things I wanted to get through today. I wanted to get to a point where you had some sense that there's another class of models out there which are often presented computationally, but at their core, what they're really doing is saying that there are differences in susceptibility to infection. And because of that, the process of infection, if there's any kind of difference, it tends to pull out those which are more likely to be infected, therefore changing not just the number of people who are left to be infected, but their likelihood of being infected. It becomes a dual process. And when that happens, even with the caution I think was offered here on the left side, generically this means that at the start things will look the same, but in the long term the herd immunity threshold will change. But perhaps even more interestingly, you'll get these distributional transformations that will unfold because the epidemic process is really sculpting who's left and who hasn't been infected. With the caution then, I guess maybe the last thought I will leave you with, and I'll put it over here, so I think we've already gone through this, and there may be some typos in my handwritten notes, but I will scan them and put them just scanned and into the files, is that increasingly I think of this infection process, if I have some initial distribution, irrespective of my parameterization, I think of different features here. That this sort of feature is a sculpting feature. The infection process somehow sculpts distributions. But that there's also social diffusion. Right? And there are other ways in which this process can be balanced by the one that potentially restores it. And on top of that, there may be other things like policy or behavior change, which could move everyone one way or another. So these different processes are modulating the distribution as we start to put on masks and take off our mask, right? As we lock down and as we open up. I can't claim in today's lecture that I have complete insights here to solve for all of these, but I find that this category of problems is quite interesting. I think it has some analogies to network models, and I haven't worked them out productively enough to tell you what I think. In this paper, we do engage with this notion of social diffusion, and you can kind of see why new things might happen. If the infection process is sort of fast and sculpts things like this, we'll reach a point where now the infection would itself die out, right? But what happens if this starts to diffuse backwards? If so, there's still some infected individuals around. Now the population is back in a position where it's more likely to be infected, even though there are fewer people, and you can get a rebound. So once you take this model, which only gives you decreasingly large outbreaks as heterogeneity increases, you can go to a model that very easily gives you plateaus and shoulders and even oscillations. Right? So including this mesoscopic approach has some advantages because you get more realistic things without adding too many features. Right? Without adding too many features. Something about the mean, something about the variance. Okay, I'm going to stop there. I'll take some questions if there are any left, but otherwise just keep in mind that today is our last day. This is really a mini course, and last night Roberto, Anna, and I went out. We couldn't go out with Renato just to talk a little bit about how the course went, just like you all go out and talk about the course, and maybe other things too. Maybe you watched, I don't know, like the CONMEBOL Championship or something. I think Boca Juniors won on penalties. I was paying attention. We talked a little bit about, what was the point of this week, or really 3.5 days. It's not a long enough time for us to go systematically through every feature. Our hope, and I hope that's the case, including the rest of the day, is it sort of activates people to get excited about different things, opens up maybe some realms that are new to you. And if that's the case, great. If there are other things you wish would have happened, maybe you wanted this to be longer, maybe you want it to be shorter. Probably the one people wanted to be shorter are no longer in the room. There's going to be a survey. ICTP-SAIFR always gives out surveys for courses. This is actually quite important. I say this for all courses that I give. It gives us as instructors, but also the team here does the logistics, a chance to understand what can be done better, what did you like. So if you like things, let us know. But if there are things that need to be improved, also let us know as instructors, but the institute know in terms of some of the logistics as well. So the feedback is always read. I'll just let you know that. So when you do get the survey, don't just delete it. Get a lot of surveys. Just spend even a minute or so would help us improve for the future, or figure out, should similar courses be offered in the future. Okay, any questions before we break for lunch? Here and then Denise. So I haven't heard. Let's go Denise and then back here. Yep. Yeah, so I think, can I say the answer is both? Because depending on the disease, it may be, if we're talking about a sexual disease, maybe it's number of contacts or protection or both. So unfortunately, I think it's both. And I'd like to think that's also an open area for investigation. Can we try to do a better job of characterizing what these distributions are and how people structure, how many people they interact with, and behavioral features, and how we can organize them, and therefore what is the impact on transmission? Right, so you have to keep in mind that there's a difference between high susceptibility and high infectiousness. So in this model, we lump everyone together. So if someone had a very high susceptibility, immediately they go to the I class, but if it's a small tail, it actually won't have a big effect. The bigger effect would be a tail in beta, right? So if we then had I be structured, and people who were infected with high epsilon also had a high likelihood of infecting other people because, let's say, beta was related to epsilon, then what can happen is you would be more likely to see super spreading events at the early part of an epidemic. Those people would be infected, and they'd infect a lot more people very rapidly. So I think there actually is a very interesting relationship. I haven't defined the distribution of number of infecteds caused by by an individual at different times in the epidemic, right? And clearly, as susceptibles depleted, you just sort of, in a trivial sense, lose the chance to infect people. But if we non-trivially had actually structured I, then some of that could show up as differences in super spreading. Yep. There and then there. Yep. Then my answer is very similar too. Okay, no, go ahead with your question. Yeah, so I look at this Harris paper, because this is an example in which we are linking the S's and the I's. So I'll go back in some ways to Denise's point. If this epsilon had to do maybe a proxy for contacts, number of people you're interacting with, and all things being equal, more infections, then if the high epsilon people are infected early, they are going to infect others early and more. And so you could actually lead to kind of a catalytic effect early. And I think that's what you were getting at and what you're getting at. So in the Harris paper, we do show how some of this effects of decreasing outcomes depends a lot on the assumption of how much of that variation collapses into I. And if it's correlated or anti-correlated, you can get different kind of answers. Yep. Yeah, we haven't yet. I mean, and again, this is part of the advantage and disadvantage of these mesoscopic models is that they lump things. The advantage is that you can then do something with the model. But you're right, we would get the same kind of answer if the difference was because it had to do with immune status and it was really a proxy for age, or if it was an activity status irrespective, and we'd get similar kind of answers. So I think it's a good question. It may vary with disease, but I don't have a conclusive answer for you. Yeah. Yes, for the little s of epsilon and the big S, which is the total number of susceptibles, yes. Sure. Yes, I'll tell you a good question. What I view it, let me write it a different way. You agree I could write it that way? That's what I think it means. So I think it means that the average attack rate is being scaled by the susceptible fraction, and that it's changing. So we have the classic thing, but now we no longer have a constant. And if this weren't squared, this would be to the factor of k. It just says that the susceptible fraction is telling us something about mean susceptibility, and it's scaling the attack rate, and that's how I think you can think about it, rather than all of a sudden now it's a different nonlinear. That's, I think, how I would write it in my head. Does that help? Correct. And therefore you're changing the susceptibility, which means you have less chance, all else being equal later on. Yep. Yeah, so we did in this paper do some approximation showing that if you discretize this, you more or less get what we expect. So they're in practice for both simulations and for just sort of demonstrations. We have, I think ultimately if you were going to try to fit the thing, you probably, discretization would also be helpful too. That's what we did here in the simulations. Yes. So that's exactly what I was trying to say with respect to these, and it's the Britain paper too that was published in Science. Other work, you have these models of heterogeneity, but because they're discretized and because they seem computational, the outcomes are quite similar. But here I'm trying, my purpose of the pedagogical lecture today was say, why does it happen? But you're right, in practice, when people want to apply it to a particular location, they tend to make groups by age or activity, and then yes, you're discretizing things. So yeah, and we show how you can do some of that discretization here and it still works. That's hopefully my point. Yeah. Yep. Any last questions? Okay. I will be around this afternoon. I do have some other things I have to do, but I will be around listening in. Thank you again for feedback, for questions, and be sure to come back at 2 o'clock for the last 2 lectures. Thanks, everyone.